Today, as we discuss the fracture of metals under dynamic loading, this is an area of particular concern to me because as a rock climber of 8 years, I don't want to fall and die. So rock climbers use a variety of metal tools to provide fall protection as they move up and down a mountain. And one of the most popular tools that we have is called a carabiner, which has a gate that allows you to clip into either an anchor point or a rope for protection. And over time, these can be subjected to different loads over sharp edges that introduce cracks right there, or they can be dropped or generally scuffed in the usage of the outdoor environment. And so the question that comes up in the climbing community often is, as your carabiner gets damaged or experiences wear over time, is it still safe for use? We know from studies that the most high concentration area for the carabiner is in this area where it is called the saddle, and that the experienced mixed mode fractures with shear and tension as well as significant T stresses playing into it. But most of these studies done are quasi-static loading conditions, which is not representative at all of the usage case. Most often these carabiners are used for fall protection or fall arrest, so there's dynamic loading involved. This dynamic loading introduces inertia forces and has rapid load rates that can affect material behavior, as well as may create reflected stress waves that may increase the stress fields at the crack tip. And then furthermore, there's often ropes sliding through these carabiners, which add friction to this whole equation and heat, and that can lead to creep. So how do you design for dynamic loading? So there is a field of study called elastodynamic fracture mechanics that's basically the LEFM of dynamic loading, and it allows us to look at two main concerns. One is whether or not a fracture will initiate due to the rapid dynamic loading, and the second is whether the material is going to tear itself apart or have unstable rapid crack propagation under load. So for crack initiation, we consider kinetic energy versus deformation energy, and this is also where our stress intensity factor for the dynamic case comes in. And then for crack propagation, to determine whether or not a crack will grow unstably or if it will arrest and stop it from tearing itself apart, we consider the instantaneous stress intensity, and this K1 is not the same as the K1 we studied in class, and compare it to the material's resistance to crack propagation. When we have high temperatures in a metal, we experience plastic behavior. This plastic behavior can lead to creep, where we see the slow growth of a crack on a macroscopic scale. The growth is stable, but there are 4 different zones of creep that need to be analyzed and considered with their respective parameters and equations. So dynamic fracture analysis tools do exist that allow manufacturers to analyze and make recommendations of when to safely retire and replace gear.